Hello everyone. Welcome to our paper presentation of complex safety mechanisms require interoperability and automation for validation and metric closure. My name is Vedant Garg. I'm principal architect at Siemens EDA. This paper has been a joint production between Siemens and Samsung Korea design team. I'm also joined with my co-author, Daeseou principal engineer at Samsung. Today we are going to be talking about what is the problem statement that we were trying to solve, what is our proposed solution for that problem. We have divided our problem and its solution into two subparts, safety analysis and safety verification. What we have done to achieve and test the proposed solution, experiments on our automotive SoC, and what is the final conclusion. So as you all know, with the increase of densities and lowering of the operating voltages in the semiconductor technologies, this has become a risk and a challenge with respect to increase in the sensitivity towards hardware failures. All the modern cars which are deploying ADAS or autonomous features, they rely heavily on their digital and analog components, and these all digital and analog components are prone to these random hardware faults. This reliance on being on the digital and analog systems have been a major concern, how validated and how reliable these systems are, and finally if they are safe. So if we were to talk about the problem statement in terms of a typical SoC representation, which is represented on the right hand side by a typical block diagram. On this SoC, I would start off by pre-RTL or RTL analysis. Then I would do an SM insertion, safety mechanism insertion based on some historical data or the previous legacy IPs that I've used. Then finally, I'll move into RTL, verifying the safety mechanism by doing an RTL or a gate level fault injection, multiple structural proofing and checks. And at the end, I will have a final safety metrics. The real reason, the real problem is by the time I get to a final metrics or an indication of metrics, it is too late and too much time have been spent in engineering for me to do more changes. To solve this problem, we have divided our proposed solution into three parts. The first portion is called safety analysis. Here we are taking pre-RTL, RTL data, and we can perform a what-if exploration or gap analysis. This analysis tells us what type of safety mechanism would be ideal for the structure that I'm analyzing. And if that structure have some gaps, this analysis can also tell us. If my IP or the design already have some safety mechanism, then I can do an assessment of that safety mechanism without having to run a full fault campaign. This gives me a very accurate early metric estimation on the choice of safety mechanism that I'm going to go with or any existing safety mechanism. Then the second problem statement that we have divided is safety verification. Here we can perform RTL or gate level fault injections. One of the major problem for these fault injection has been an optimized fault list. So during the safety analysis with the safety mechanism that we are using, we will already be generating an optimized fault list. This will feed into our fault injection engines automatically and will provide us the fault injection results along with other structural proofing and checks. This truly is reducing the overall iteration because through early metric estimation, I already have some insight without having to run fault campaign, how much coverage is expected. And to make that proof, I am reducing my fault injection iteration. During these entire process of safety analysis and safety verification, I am already able to generate a final automated FMEDA and safety metrics, which can be used as final reporting. So again, our problem statement, we divided that into three major portions: safety analysis, safety verification, and safety metrics. Using these three fundamental divisions, we were able to generate a overall safety workflow. Um, so we take our automotive SOC, and in the generate section, we will be analyzing the complete SOC structure. We will be able to generate an optimized fault list with respect to individual failure modes and with respect to individual fault injection engines that we are using in the next step. We have multiple algorithms and things that are already covered in this generate section. For example, safety aware, optimization in the fault list generation, fault collapsing, fault sampling, fault propagation. Everything gets saved into this functional database that we created for the safety workflow. This functional database is automatically read by the fault injection engines, which can be either simulation, emulation, or formal. And our database is smart enough to feed the simulation based fault list to simulation engine, emulation based fault list to the fault emulator, and formal based fault list to the formal engine. And these three engines can run independently, mutually exclusive to each other, and then they can save their results into the same database again. Now, this database will automatically merge the results that we have captured from running one or three different fault injections, and then we will be able to calculate a final metric automatically. So again, we took the same approach of our proposed solution: generate, which is generating an optimized fault list using multiple algorithms that we have at our hand. In the inject, we are automatically injecting those fault lists into their respective engines. And in the report, we are automatically getting the final metric report. How we are optimizing this workflow, as we discussed, we perform early RTL analysis. We do generate the fault list, which can be optimized for individual fault injection engine. We have capability to generate a safety mechanism or safety aware fault list. We do perform shallow fault collapsing. We will identify all the faults that do not propagate. And of course, we have built in statistical random sampling and architectural vulnerability factor like algorithm in our engine so that we can get these sampled fault lists ahead of time. And in this early analysis, we are also improving our overall structure by using some formal techniques for determining the testability of the faults. Using the automated fault injection flow, we take this generated fault list and we automatically distribute into these three engines, which saves back into the database and get the final metric reports for us. This complete flow is described in the ISO chapter 26, ISO 26262, chapter 11, which describes the fault classification at semiconductor level. So let's discuss safety analysis a little bit more in detail. Under safety analysis, we are taking the RTL data and we are performing the what if analysis. What if analysis or exploration gives us an insight into what will happen if I were to use a custom safety mechanism or a safety mechanism of my choice what would be the effect of it over the analyzed area or the overall design. And I can get this metrics without having to run the full-blown fault campaign. This early indication of metrics is very powerful, as it saves a lot of time, engineering time in hand. And this gives me an indication of what type of coverage I'm looking for my overall SOC, if I were to create these safety mechanisms in my design. At the same time, while I'm exploring or analyzing the existing safety mechanism, I'm able to generate a fault list which utilizes multiple failure modes, which have capability of tagging a fault list for simulation or emulation engine. It has direct integration to the validation tool, and I can model multiple failure modes while generating this fault list. What As a final byproduct of safety analysis, I also get to generate the overall FMEDA, and I can generate this FMEDA at the analysis level where we don't have the fault injection done, but this analysis engine will be able to tell what type of overall metrics I'm looking at, and it can be divided into multiple subparts which are leaning into a part, and we can combine multiple parts together at the SOC level. Safety verification using Kaleidoscope is our way of doing the fault injection. We uses a highly performing concurrent and distributed fault injection model for doing the fault injection run. Uh, it starts with an optimized fault list, which is of course given to us by safety analysis, and then the fault injection manager for simulation will automatically divide into multiple parallel and multi-threaded jobs. Um, at the end of fault simulation, we will get a final detected report, how many faults were able to be detected for stuck at 1, stuck at 0, or both. And based on that, we will be able to calculate a final metrics. Now we can use the entire reporting structure for more debug. We can do fault propagation or waveform compares or do debug of non-detected faults. And we should be able to get all that data through this simulation engine. In safety verification, we also used emulation as a platform to perform fault emulation. And we were able to perform the complete mission mode circuit, safety circuit verification for stuck at transient SEUs and bridge faults. We were able to define the overall effectiveness of the safety mechanisms. And this was the second engine that we automatically divided our fault list structure to. Now let's talk about the actual experiments on our automotive SoC. So this is a typical representation of our SoC that we used. The block which is highlighted in green, we called it a safety island, and we will be focusing majority of the experiment on this particular block. To give you more context on this block, the size of the block is around 890K registers, close to 46.5 million gates. Uh, some of the major blocks under this particular safety island is the CPU cache, around 215K registers, bus peripheral, the complete structure, around 470K, and FMU around 33K block. To show you more a little bit on the safety island block, this is a typical representation of our safety island block. It has a CPU core cluster, which has memory, the bus, the FMUs, um, In terms of safety mechanisms, we have model software test library. We have modeled some ECC, watchdog timer, and then end-to-end protection on our buses. The CPU core is coming from a leading soft IP provider, and then we have the Cortex R52 block. It has around 13 sub blocks, and it is consisting the software test library, ECC, watchdog timers, and then we were able to generate like overall fault list with respect to these safety mechanisms for all of the blocks, and we used fault emulation for this particular block to do the verification. So these are our results of fault emulation. You can see that for CPU core and cache divided into 13 sub blocks, we modeled the overall fault list generation, and then we are showing you results on one sample data. So one random sample pulled out of all the faults, total number of faults that can happen, and we are showing you a result on that sample. Of course, to completely verify, we have done multiple samples based on the ISO 26262 spec, but this particular data that you see is for one sample. So what you see here is that, for example, on sub-block 1, we had around 85,000 faults. The overall fault distribution in the random sample was around 13%. For example, for sub-block 1, that there are 85,000 faults that can happen in sub-block 1, which represents a 13.5 fault distribution out of the total number of faults, which is around 636K. We pulled a random sample, and in random sample we found there are 604 faults from sub-block 1, which is representing around 12.63% fault distribution, which is around the same fault distribution with respect to the full exhaustive fault list. And we were able to detect around 315 of these 604 in this particular sample. So our detected fault ratio with respect to sub-block 1 was around 52%. And similarly, we have exercises done for all the 13 sub-blocks. And then we have modeled multiple random samples, and we have collected the data in the same way. Overall, we were able to detect faults, and if I were to categorize the number of faults which were detected by safety mechanisms, ECC correctable, ECC uncorrectable is around 17.5%, 16.8 and 0.74. Software test library SM1 around 80%, watchdog timer to be 1.76%. So this is the overall fault distribution with respect to the safety mechanisms. If I were to talk about the classification of these faults, one sample that we just show you, previously on the previous slide, had around 63% detected observed fault and 12% undetected unobserved fault. These were the one of the two major categories, and the third major category was not injected fault of 15%. So this puts us close to 65% detected fault ratio with a margin of error of 1.19%. Now, we did perform stimulus gating to identify the not injected fault, and we performed some post analysis on this undetected unobserved fault as well to get some more visibility and to debug what is the overall what should be the overall classification of this category. So in the post analysis, we performed analysis of this undetected unobserved fault, Using cone of influence analysis, we had signal back propagation, we had safe fault configuration that we did in our UU or undetected unobserved analysis. After doing this post analysis, we were able to reduce the number of undetected unobserved fault to 280. So this number of faults that we were able to process in this post process were mapped to either safe faulted logic, or conservatively, we remaining faults in these 280 faults were termed as residual fault, to be on the very conservative side. So with that, on this in this particular portion, you can see our detected observed portion was increased to 77% as we performed post analysis on the UU fault and the not injected faults, and we were able to classify them either safe or residual in this particular case. In the bus structure, we used the simulation model to perform the verification. We used our analysis engine safety scope to generate the overall fault list, and used kaleidoscope simulation engine to perform concurrent simulation. You can see that in the four scenarios described below, we were able to increase our fault detection ratio with respect to each scenario. We started with 3%, 5%, 9%, and at scenario number 4, we are at around 42%. What we are utilizing here is multiple approaches and multiple optimizations coming from the analysis side, which are directly helpful in our simulation model. Things like stimulus grading to perform early analysis in terms of whether these faults will be able to be injected in the scenario or not are really helpful. At the very end, as a result, we were able to calculate the overall final metrics for CPU block with respect to all the samples that we analyzed and performed verification on. Our overall DC permanent is 91.38% with a margin of error of plus minus 1.29%. Keeping the conservative margin of error on the negative side, we still are above 90%, which was our initial target to be SLB for CPU subblock. Now, the fault injection of bus is still in progress. We have not finally concluded on that simulation, so that those results are still work in progress and will be part of our future work. The FMU block, the fault management unit, will be utilizing the formal technologies to be verified by formal. So our overall result consisted of three step flow: the fault optimization technique, combining the fault injection engines with automation, and reporting the final metrics using the same database, which is reading the injection reports. As a conclusion, I would like to describe that this comprehensive approach of verifying such a large scale IP with just one fault injection engine is non-practical. It will not be, we will not be able to get that result if we were to use only one fault injection engine. For a design like system on chip test case that we showed here, it is recommended to use multiple fault injection engines, the optimizing technique that we talked about, and automation around those optimization techniques to significantly reduce the time complexity and the error that can happen in the manual feeding in codes. We closely worked with the product team and the methodology teams, with Siemens EDA and Samsung. And this type of collaboration is very, very crucial for a project this size, and coming up with an overall optimized workflow. Without each other's help, these type of methodology and overall safety workflow are not possible. Conducting safety analysis before the fault injection is absolutely crucial. It saves a lot of time, and therefore, as a final conclusion, we were able to demonstrate that how to optimize your fault generation, and then how to involve your multiple fault injection engines by using a common database to give you the overall enhancements and optimizations that are needed for this type of project of this scale. And with that, I open the floor for some questions. Thank you.